Okay, so let's start with the global positioning system basics. So we see three segments which are the main parts of the system. So the space segment with the satellites, the control segment with the satellite monitoring and control, and the user segment with the GPS user devices. So the space segment, as I said, it consists in the constellation of satellites. The nominal GPS constellation requires 24 satellites, which are scattered on 6 orbital planes, every 60 degrees from each other one. So you have the 360 degrees around Earth. 4 satellites are available on each plane with an unequally distribution to provide fault tolerance. They are on a semi-major axis of 26,560 kilometers, which means their altitude is 20,200 kilometers. The eccentricity of the orbital planes and orbits is less than 0.01, so it's almost circular. And the period, which is the time that one satellite takes to run all around the Earth and go back to its first position, is around 12 hours. This means that each satellite is constantly moving at 4 kilometers per second. That's quite fast. And it produces problems that we'll talk about when we deal with the control segment. So currently there are around 30 satellites in the constellation because there are older ones which are still operational. So actually, when you put a satellite in space, you certified and built it to for a target life cycle, and it can exceed this target life cycle. So if it's still operational after this target date, you still put the new one in space because you have no guarantee on the operations of the old satellite. But as long as it's still operational, you will use it to improve further the accuracy and the precision of the system. So it provides redundant measurements and fault tolerance, therefore improving the reliability and the availability of the system. This is how almost everywhere on Earth you have at least 6 satellites within line of sight instead of 4. That's which would be the minimum number of satellites used for providing a location. Less than 4, you cannot have real good location determination. The control segment, it's a segment which is completely hidden from us because it's the internal operations of the system. So it's composed of monitoring stations which receive orbital data. Actually, they track the satellites which are in orbit and they measure their deviation compared to the models in the system. Then the master station will process all the data from the monitoring station. It will update the times and orbits of the satellites accordingly to what their real status is. and using the ground antennas, which act as uplink stations, so they send signals to the satellites from the ground. They will transmit the updates to the satellites. So it's said that the control segment monitoring control center is in the Schriever Air Force Base in the Colorado, but well, it's not. It may not be true because it's a military thing, so this tends to be a lot of secrets about that. So it's operated by soldiers from the 2nd Space Operations Squadron. They use the monitoring stations to receive the tracking data. Their systems will update the satellites through the ground antennas, and the updates will especially include synchronization of the atomic clocks very close from each other, so the satellites' clocks must be synchronized to a few nanoseconds from each other, else the system will completely derail. So 1 nanosecond error, which it means 30 centimeters error when you compute the distance between the satellite and the user device. They will adjust the ephemeris of the satellite's internal orbital model, because you need this information from the user device to point of view to compute your location precisely. And since there is some noise on the measurements from the monitoring stations, they use Kalman filters to smooth the inputs to get something a bit more regular, to be able to put clean data in the satellites. So the problems that you can encounter from the control segment point of view might be satellite trajectory change, for instance. So it's not precise in the GPS standards, but they found a hack in the standard, which is to mark a satellite as unhealthy, so that the user devices won't use this satellite information to compute their location. Then they move the satellite trajectory, they track the new orbit, and when it's stable, it's okay, and the ephemeris is updated and uploaded to the satellite, it can be marked healthy again and used by the user devices. So there is a problem. The main problem from the control segment and the ground segment point of view is to update the satellite clocks, because each satellite has an atomic clock which is very precise, but with the speed at which they move and different gravity than the user devices, the relativity theory tells that time doesn't flow the same speed as on Earth, so we have to fix this periodically for the system to be able to operate. That's why the GPS time standard is very precise, and when you are using a GPS chip inside the device, its clock can be used to set your system clock with a very precise date and time that cannot be achieved even with something like NTP, the Network Time Protocol, which has not the same reliability than the GPS time. So now the user segment, who is it? So it's the army, it's fleet management, it's agriculture, navigation, emergency services, and finally customers. This means you. So usually when we talk about GPS, that's what we think about, even if it's quite the easy part of the system. So a GPS chip doesn't do many things, while on the other hand, maintaining a full satellite constellation and tracking it, updating it, and so on, it's quite a complicated job. So let's talk about the receivers. First, they come with various qualities, but they at least share some functions, which are to identify each satellite in sight, compute its distance between its distance towards any satellite in sight, and then using n-lateration, compute the location, the location of the user device. Then there are additional functions which are not on all of the GPS chips and software, to ease or improve the positioning, to add services, so routing, integration to communication systems, and so on. But again, the core features of a GPS chip is to identify the satellites, based on those satellites messages to compute the distances between itself and the satellites, and then using the distances and the satellites locations to use n-lateration to provide its location. So to do so, the GPS receiver is composed of an antenna which is tuned to the satellite frequencies, because after going through all of the atmosphere, its RSSI is very low. The receiver has a processor to compute its location, and a highly stable clock, which is based on a crystal oscillator, which is far less precise than the atomic clocks of the satellites, but which synchronizes itself with the n-lateration computation that we'll see at the end of the lectures. It is defined by its number of channels, which is the number of satellites that can simultaneously be tracked. So the first GPS chips could only track 4 or 5 channels and satellites. And nowadays it can range from 20 to more than 12 to more than 20. Why so many? Because due to compatibility reasons, the GPS now can work alongside with GLONASS and Galileo, so you may use 5, 4 or 6 satellites from the GPS alongside with satellites from GPS augmentation system, and GLONASS satellites and Galileo satellites. So it's a lot of satellites together, so you have to have many channels to keep track of everything. So the GPS chip must transmit its data, its location, to a computer or a smartphone, either by the NMEA protocol, which is interesting because it allows open source tools such as GPSD to use its information, or through proprietary protocols such as SURF or MTK. And it can transmit those information on serial connections, USB, Bluetooth, and so on, or in the case of smartphones, it's directly inside the chip, which embeds everything. The satellites and the user devices communicate through several frequencies. So first one is L1 near 1500 MHz with coarse acquisition and encrypted PY code. So the encrypted PY code is reserved for the US military. And the L2 frequency, which is reserved for the military use. It's around 1200 MHz. So with both frequencies you can fix some of the errors due to the atmosphere transversal, and that's why in part the military version of the system is more accurate than the civilian one. So how does it operate? Each satellite broadcasts a navigation message at 50 bit per second, so it's very slow because you have to be able to decode the messages from devices which are more than 20,000 kilometers from the satellite. Each satellite message is composed of 25 frames which last 30 seconds each, which means that to receive the whole data it requires 12.5 minutes, which is long when you perform a cold start. Each frame is composed of 5 subframes, which has 300 bits, and each subframe of 10 words of 30 bits. So the frame structure starts with a TLM, telemetry word. It marks the beginning of the subframe and allows to synchronize with the navigation message. It is then followed by the handover word, which contains timing information, allows to identify the subframe and to tell which time the next subframe, which actually is the actual subframe actually was sent, so the rest of the subframe. The subframe 1 contains clock correction data with the status and accuracy of the current satellite, which is the satellite clock precision and its relation to the GPS global time. Then subframes 2 and 3 contain ephemeris data of the satellite which sent the message. So it's the current satellite precise orbit, which is updated every 2 hours and valid for 4 hours. And the older the ephemeris, the longer the warm start. Warm start means that you already have the almanac, which is the global and precise orbit information about all of the satellites, but you do not have an ephemeris data which are still valid. So it's what happens when you restart the GPS after several hours without using it. Then subframes 4 and 5 contain the almanac data, which are coarse data about the orbits and the status for all of the satellites. So each frame is 1 on 25 on the almanac data. When you have no almanac, so it's really old, more than maybe 1 day, you perform a cold start, which will take up to 12.5 minutes to get all of the data from zero. The purpose of the almanac is to acquire the satellites, to relate the GPS time to the UTC time, and to allow single frequency receiver to correct some ionospheric error with a global ionospheric model. The ionosphere is one of the high atmosphere layers which impact the wave propagation. Then the chip must decode the coarse acquisition signals, which have a gold code of 1023 bits with 1025 different codes. So since you have a Doppler shift with the satellites moving very fast, it requires the almanac to take that into account. And your coarse acquisition signal doesn't have all of the data, at least up until the year 2000, it didn't have all the precision. So then how does it compute the distance, the location? So you have your signals, you have the time. From the time you get the distance between your GPS chip and each satellite. And then you have to compute the location. So you hear a lot of triangulation to determine the location of the chip, but it's not the proper method. It's not what the GPS use. Triangulation is based on angles, which are easy to get when you are manually measuring angles and computing the location, but it's not what a system like the GPS can easily do. So you have no reference to give angles, so we use multi-n-lateration, which is a distance-based method. It's good because we can compute our distances between the satellites and the receiver chip. It's easy to automate. There is an iterative method which implies a lot of calculations, but that's what computers and electronic devices are good at. But it's hard to measure its accuracy because there are errors. So of course it's simple if you have proper distances, the full circles here. For the location you have only one intersect, which is easy to compute. But in real life you have estimates, so the dotted circles here, and you have no unique intersect, so you have to estimate where the location must be. So for instance here it's closed from all the circles, so it's not exactly the real point. Well, that's the problem with real life and physics and measurements. So how does it work to get the distance between satellite and GPS chip? You multiply the time it took to go from the satellite to the GPS chip for the signal by the speed of light, c. So this time must be precise because if you derive from 1 microsecond, you already have 300 meters error. It's huge for positioning. So that's why you need synchronization in the operations. So as I said, the satellites have atomic clocks which are very precise with a low deviation but cost a lot. And the problem is the relativity theory, because moving fast in different gravity, their time is very precise but does not flow the same speed than our time on the ground. So on the other hand, the receiver has a quartz clock. It's not expensive, of course, because you put this in sometimes €1 devices, and it's not precise compared to the satellite's atomic clocks. So being able to measure the deviation and fix it is critical. So that's why we compute this formula. So this is an example with 4 satellites. it means that the real distance between your satellite, actually the distance estimate between the satellite and the device is the real distance between the satellite and the device. So this is the x, y, z, u for the user device, and x, y, z, s1 for the first satellite. It's the same for the other ones. Plus the speed of light multiplied by the difference of time, so the lack of synchronization between both devices, the satellite and the GPS chip. So you have to solve this system, which is not linear because it's quadratic. Then you had some other things in the real equations. So you add the atmospheric error, which is related to the impact of the ionosphere and the troposphere. The ephemeris error, which increases the older the ephemeris, and other errors. So these ones cannot be processed because they are not systemic, while these ones can be processed and fixed. So the receiver requires at least 4 satellites to determine its location, because 2 satellites will give you an intersect which is a circle. A third satellite gives 2 points, and the fourth satellite narrows it down to 1 point. The satellites must be in sight of the receiver, and the more satellites on site, the better the location accuracy and precision. So, of course, the current layout of the satellites in relation to themselves impacts the accuracy. So you have an indicator which is based on the satellite spread geometry, which is called the DOP, dilution of precision, and it is declined in GDOP, VDOP, HDOP for the global dilution of precision, the vertical dilution of precision, and the horizontal dilution of precision. So if we look at the pictures, this here is layout of the satellites, which is bad for the accuracy because the satellites are very close to each other. So their signal, since you need at least 4 satellites, they are not, you have not 4 very different signals, so it's closing to having only 1 signal. So imagine, it's not possible, but imagine you have 4 satellites which are on the same, exactly the same spot. It's like having only 1. Here they are more scattered. It's very good because their distances and locations are far from each other, so their information is not collinear, and it gives a lot of significance to each satellite distance and location. So the GPS system gathers the variances of the x, y altitude and distance, which is the time variances and errors. While using everything, you have the global DOP with only x, y, and z. You have the point DOP. With only x, y, you have the horizontal DOP. With the only the z one, you have the vertical DOP, and with the distance, so the time, you have the time DOP. So as I said, the satellite position when you compute your location, it greatly interferes with the location estimation. So the instant quality of the positioning bound to the current satellite's locations is given by the GDOP, which should be close to 1 to provide a good accuracy and precision of the location estimate. So let's look quickly at the errors that can be encountered by the GPS system. So first you have a table which lists errors in the space segment, the control segment, the user segment, and the total. For the precise positioning system, which is reserved for military use, the standard positioning system, which is the current open to everyone's system, and the selective availability, which was the previous system when a bit of the signal was scrambled by the US military to provide a degraded service to everyone else. So clock stability, satellites, and other errors are the same for all systems, all services quality, and only the selective availability adds a big error to the selective availability system and service. In the control segment, you will also have the same errors because they are systemic for every use. Then in the user segment, you have less error for the ionosphere error, but a bit more for tropospheric, which is a bit fixed and the multipass too by the use of the two frequencies for the military, US militaries, with the precise positioning system. Other errors are similar, which gives precise positioning system global error of 6.6 meter, 8 meters for the standard positioning system, so the one we use nowadays, and 33.3 meters for the selective availability, which is quite huge when you try to navigate through roads and so on, or you are by foot. You can, the error is enough to miss the correct address, the next stop, or else. So this was bad accuracy, and we'll see that what it led to. So in real-time GIS constraints, you generally have 15 meters errors, but it's hard to estimate because your navigation system and software will usually use the road network to fix a part of the errors to put you back on the road, for instance. And it can be improved with differential GPS with longer measurements, but an error which can reach about 10 centimeters for static measurements. The GPS is subject to interferences from jamming, which is something malicious and that someone wants to disrupt the GPS. Other radio waves in the same frequencies, canyon effect, for instance in big cities with big skyscrapers, these ones can block the signal. The sun and its activity can have some adverse action on the GPS signals, the weather too, so it doesn't go through with the same quality through rain and so on than in clean and good weather. The time of the day, since the GPS satellites will be more or less well situated for providing your location with accuracy. Multipath given all of your environment. So all of this interferes on the GPS accuracy. So with all of these concepts and ideas in mind, we can draw some limits of the basic GPS. It provides a good relative position, but it requires a free sight to the sky, so that's why indoors we have to develop other systems, such that we did in the first part of this module. It depends on only one provider, so a few years ago I told that relying on the United States of America is not always a good idea. We know that they spy on everyone in a big scale through social networks, your emails and so on. As soon as you are in USA-based service, and today we can tell that with someone like Donald Trump at the head of the United States of America, it's becoming increasingly complicated and maybe dangerous to rely on a North American service to get our devices located for some of the strategical and critical applications. Furthermore, the GPS has no integrity for the civilian use, and its civilian applications are easy to jam. So all of these shortcomings are supposed to be addressed by Galileo, but it's still we are still waiting for the full system to be operational. As a conclusion, the main advantages of the GPS is to be the fully operational system. So actually there is a GLONASS now which is fully operational, but it has the same drawback that we have to rely on the goodwill of Vladimir Putin to be able to use the system. So not always a good idea. It provides a good accuracy and a good precision, especially when using existing augmentation systems that we'll talk about in the next video. But its drawbacks are to be under USA military control and only provide one civilian mode without quality of service and guarantee of service.